In section 2.3, we're going to study the concept of continuity. Continuous functions are ones whose graphs can be drawn without lifting your pencil off the paper. So for example, y equals x squared would be an example of a continuous function. And the greatest integer function, sometimes called the step function, would be an example of a non-continuous function because there are a number of breaks in the graph here. So types of discontinuities. I'm going to watch a quick video outlining different types of discontinuities. Okay, so we learned three different types of discontinuities in the video. And this first one at x equals -1, we call that a jump discontinuity because the limit from the left doesn't equal the limit from the right. At x equals 0, we call this one an infinite discontinuity because on the left and the right, the graphs are both approaching positive infinity. And at 1, we're going to use the term removable. I know the video said both point and removable, but we're going to use the term removable for those types of discontinuities. All right, for continuity at a point, there's a three-step process for a function to be continuous at a point. And they kind of touched on it in the first video, and these are the three. So if a function is continuous at a number a, first of all, the function at a has to be defined. The limit as x approaches a of that function has to exist, and basically statements 1 and 2 have to equal each other, and we saw that in the first video. The limit as x approaches a of my function has to equal the function at a. So let's take a look at this example, and let's see what is true. Both the limit as x approaches 6 from the positive side of g of x and the limit as x approaches 6 from the negative side of g of x exist. Well, from the approaching 6 from the right side, I'm approaching a value of -3. Approaching 6 from the left side, it does not exist. It's going to infinity. So therefore, we cannot say the limit at 6 exists. G is defined at x equals 6. That is not a true statement because there is no solid dot on 6. G is continuous at x equals 6. No, that is not true as well. And neither could you really say that top one because the limit is unbounded here, so there really isn't a limit as x approaches 6 from the left. So the answer really to this question would be none of the above. Okay, in our next example, we're looking at the graph of m of x, and we want to explain why m of x is discontinuous at the following. So we want to use the three-point definition and explain where it breaks down, and we want to classify each discontinuity. So in the first one, we're looking at x equals 3. So we're dealing with x equals 3. So the first thing I have to do is find out, is there a value of the function when x is 3? Well, if we look at m of 3, there is no value of the function. So this does not exist. And there is no limit as well. And if we looked at the vertical asymptote at 3, so that would be an infinite discontinuity. So this breaks down at the first step of the definition of continuity. We take a look at the next one at B. They want us to check it out at x equals 1. So at x equals 1, is there a value of the function at 1? Yes, the value of the function at 1 is 1. Is there a limit as x approaches 1 of my function m of x? And if we look at 1, the limit from the left does not equal the limit from the right. So this would be part 1 of the definition. This would be part 2. So this thing breaks down at part 2. And this type of discontinuity is a jump discontinuity because the limit from the left does not equal the limit from the right. In part C, we are looking at when x is -1. So first of all, is there a value of the function at -1? And if we look, no, there is not. This doesn't exist. And if we look at the graph, there is also, it breaks down in statement 1. If we look at the graph, there is a hole in the graph, and it's a linear function with a hole. So this guy would be considered a removable discontinuity. The last one, D, we're looking at x equals -3. So first of all, is there a value of the function at -3? So this is part 1. At -3, the value of the function is 1. Part 2, is there a limit as x approaches -3 of m of x? And yes, there is a limit. That limit is 0. And part 3 now, does the value of the function at -3 equal the limit as x approaches -3 of my function? Well, clearly this is not true. So therefore, it's not continuous. And again, it would be considered a removable discontinuity at that value. Okay, sometimes a function can be continuous over a particular interval. Okay, so let's say that this graph goes on forever and ever in the negative direction. Similarly, we'll say this graph goes on there, and this one here, and this one here. So these functions would be continuous over a certain interval. So for this particular graph, it would be continuous from negative infinity up to and including -2, union with a round bracket on 2 to 4, not including 4, union with 4 going on to infinity. So functions can be continuous over particular intervals, and we see that in this particular graph here. Okay, let's take a look at an AP question from 2003, and it's asking us, or gives us this function, and they want us to explain, is the function continuous at x equals 3? So again, we have to go through the 3 parts of the definition. So first of all, we want to evaluate f of 3. So to evaluate f of 3, I'm going to use this equation because that's where x equals 3. So this is going to be the square root of 3 plus 1, which is root 4, which is going to be 2. Step number 2, we want to calculate the limit as x approaches 3 of my function. And since my function splits at 3, I have to do the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. 3 from the left, that's less than 3. I use this equation. And we found if I plug a 3 in there, I get 4. The square root of 4 is 2. From the right, I use the equation 5 minus x. 5 minus 3 is 2. So yes, there is a limit at 3, and it is 2. So statement 3 now, we would say the function is continuous at x equals 3 because the value of the function 3 equals the limit as x approaches 3 of my function. Those both equal 2. Okay, I encourage you to pause the video and try the same example or similar example from the 2011 AP exam. Again, we just need to look at part A right now. Okay, I'm hoping you had a chance to try this one. So again, they're asking us to show the function's continuous at x equals 0. So we're not trying to prove whether it is or isn't. They want us to show. So that's indicating to us it is continuous. We just have to go through the 3-point definition. So first of all, figure out f of 0. Again, I'm using this part of the function. So it's going to be 1 minus 2 times the sine of 0. Again, knowing your unit circle, the sine of 0 is 0. So f of 0 is equal to 1. So now I have to figure out the limit as x approaches 0 of f of x. So again, I would have to do the limit as x approaches 0 from the left, the limit as x approaches 0 from the right. So from the left less than 0, I'm using the function 1 minus 2 sine x, and we found that that equals 1. Coming from the right, I'm using e to the negative 4x. If I put a 0 in, I get negative 4 times 0 is 0, and e to the 0 is 1. So therefore, the limit as x approaches 0 is also 1 because the limit from the left and the right are the same. So part 3 now, we can say that the function is continuous at x equals 0 because the value of the function at 0 equals the limit as x approaches f of x, and those both equal 1. Okay, that is the end of the first part of continuity. We'll just pause the video and we'll start this next section in the next video.